Okay. So, is there anyone here who wasn't here last week? Swastik? Okay. You were here last week? You were, okay, so Swastik. Okay. Well,
I was tired last week. Does that count?
you're tired. Yeah, okay. So, okay, so I'll review it to the extent that I'll show roughly how the argument went. And so what are we going to do today? We want to show that bounded independence fools, say, degree 2 polynomial threshold functions. Okay, so just a reminder. So the definition is that f, say, minus 1, 1 to the n, well, even to minus 1, 1, is a degree d PTF. This is polynomial threshold function. If f of x is equal to the sine of p of x, where the degree of p is at most d. Okay. And what we wanted to show was that the expectation over x uniform, or let's say minus 1, 1 uniform, I don't know how to write this, of f of p of f of x minus the expectation over x coming from some k-wise independent distribution. We want to show that this is less than epsilon, and we want to understand what value of k guarantees this. Okay, so last week we showed that k can be just 1 over epsilon squared.
You do assume that the marginals of x are the same in both expectations.
Oh, yeah.
What is in the model? It's a uniform distribution. Oh, the k-wise independent one.
Yeah. Any k bits look like they're uniform on all 2 to the k possibilities. So this was something that was first proven by Diakonikolas, Gopalan, Jaiswal, Servedio, and Viola. And I showed you a proof last week that's based on FT-Mollification.
You showed us
for d equals 1. That's right. And there's this notion of a regular case where no coordinate has too much influence. So the largest coefficient in this polynomial is at most tau. Then you call it tau regular. So we use the same reduction that Diakonikolas et al. Used to reduce to the regular case, and I showed you the proof for the regular case. And in the regular case, if you have sufficient regularity, there's no tilde here. The tilde comes from the reduction. So. Their L2 norm is 1. Okay. Yeah. Okay. So today, what I'm going to do is k equals poly 1 over epsilon for d equals 2. And as a warm-up before that, I'll show you the intersection of half spaces. It's an intersection of m half spaces. So I want to fool the indicator function of this set. And if we have, well, depending on how much time is left, stable distributions. So instead of having uniform random bits, instead of having a plus minus 1 to the end, we're going to have.
But is it clear why the intersection of m half spaces is a warm-up for the d equals 2 case?
No, it's not. It's a warm-up only in the sense that the technique that I'm going to show you to solve this is similar to the technique to solve that, except this is easier to demonstrate. Okay. Or, yeah, I mean, basically there are many new things that have to come in to solve this one compared to what I showed you last week. and I don't want to show you them all at once. Okay, so stable distributions for d equals 1. And this has streaming applications. So in particular, it gave the first optimal space algorithm for L1 estimation in a data stream. Okay. So I guess we'll get there, but yeah, we'll get there. But basically, Gaussians have the property that if you have the sum of AI GI, where GIs are independent Gaussians, that's distributed like the L2 norm of A times a Gaussian. So p-stable distributions have the property that the sum of AI, let's call it HI, is distributed like the LP norm of A times a times H times a p-stable random variable. So in particular, they don't have bounded variance, because if they did, they would satisfy the central limit theorem, and you would have something like that. So, okay, yeah. So heavy-tailed, they're heavy-tailed. They're very heavy-tailed. Good. So let me just recap kind of one line from last week's proof. Yeah. Better lower bounds? I think the best known lower bound is d squared over epsilon squared. So it's not known that d needs to be in the exponent. Have to. Right. I don't remember offhand. I vaguely remember products of majorities of, like you block variables and majority and product, but don't quote me on that. I'd have to check the calculation. Oh, you mean for 1 over epsilon squared? So I think you all had a paper where you considered more general distributions. So in the proof that, yeah. Well, so from the proof from last time, really what you needed is just that you have bounded moments, and you have anti-concentration, and I think those are the only. Oh, I see. Okay. Yeah, so I guess I'll need various things. Okay. Yeah, so I guess you just need bounded moments. Okay. So let me just recap what the proof looked like from last time. So we had this theorem, which I'll call the FT-Mollification theorem, which said that for all theta and for all positive c, there exists a function I tilde theta infinity c mapping the reals into the non-negative reals. Okay, so this thing you should look at as being an approximation of the indicator function of the interval from theta to infinity, such that so I'm going to write this up more formally later. I'm just trying to recap. So one was that we had bounded kth derivatives. So it was at most 2c to the k for all k. And then the other thing was that we had some bound that said I tilde and I are close to each other. So for all x, I tilde c of x minus I of x is at most the min of, so it never gets more than 1 apart. But if you're far from the boundary, you can do better. C squared times x minus theta squared. Okay, and then the proof went something like, let's look at the expectation of over x So x is uniform. X is going to be uniform, and y is going to be ky is independent. We look at the indicator function evaluated at a dot x. We say that's close to the smooth function, which is close to the ky is independent case. And we go back to the original function. These are all indicator functions of this set from theta to infinity. Okay?
This uses the regularity of A already.
Yeah, so I'm assuming A is regular. I needed that A was regular in this inequality. And similarly in this one. Okay, so what goes wrong if I tried to do this argument with a degree 2 polynomial? Okay. So the thing that goes wrong, well, okay, so let's see what happened here. In that inequality, I had, so let me call this inequality 1, 2, 3. In inequality 1, I just said that the difference in the expectations is at most the expectation of the difference. And then I said, well, let's just look at how far this is from the boundary. So it might be epsilon from the boundary, the probability that a dot x minus theta is less than epsilon, in which case I know that I'm never off by more than 1. Otherwise, my distance is between 2 to the s epsilon and 2 to the s plus 1 epsilon for some s. So the sum over s times the probability that this distance is less than 2 to the s epsilon times O of 1 over c squared times 2 to the 2s epsilon squared. Okay. So the proof last week, this forced me to set c to be 1 over epsilon to cancel that. There's a 2 to the 2s here in the denominator, but the probability that you're less than this is 2 to the s epsilon. So this became a geometric series, and it became dominated by this, which was just O of epsilon. Okay. So it turns out that for degree d polynomials, so this is degree 1, and for degree d, there's a theorem by Carberry and Wright which says you can get something like d times epsilon to the 1 over d. Okay. So this is not that big of a disaster for degree 2 polynomials. I mean, basically, rather than just set epsilon to be epsilon squared, and then this will be epsilon. Okay, so. Oh yes, that's yeah. So, right. So, why was this O of epsilon in the regular case? It's because in the regular case, Bernoulli tells you that your distribution is close to what a Gaussian would do, and you know a Gaussian is anti-concentrated. Okay. So what Raghu was pointing out was, so Bernoulli is for degree 1 polynomials. If you move to higher degree, you need to use the invariance principle, which tells you, so this is Mossel, O'Donnell, Oleszkiewicz. It tells you that if you're regular, so no coordinate has too much influence, then you're close to a polynomial evaluated. Polynomial evaluated at plus minus 1 is close to being evaluated at Gaussian. Okay. So if you have sufficient regularity, I'm not specifying some parameters right now, but if you have sufficient regularity, then this will be true. Okay. So in particular, this is what a Gaussian would do. So you would set epsilon to really be epsilon squared, and then this would just be O of epsilon. Okay, so that it's not so much of a disaster. You know, you wouldn't get maybe 1 over epsilon squared. You'd get some other polynomial 1 over epsilon. So okay, so this is not inequality 1 is not the thing that's troublesome. What is going to be troublesome is inequality 2. And let me show you why that's the case. So let me write x is a dot x and y is a dot y. Okay. So how did inequality 2 go? That was Taylor's theorem. Since we have a function with bounded derivatives, our Taylor error is small. We expanded the function to be a Taylor polynomial plus error. The polynomial parts canceled, and we bounded the expectation of the Taylor error. So how did that go? It said, well, I tilde c of capital X is equal to some degree k minus 1 polynomial evaluated at capital X. Oh, I'm already using p, I guess, as the polynomial I care about. So let me just write it. Some degree k minus 1 polynomial evaluated at capital X plus minus an error term, which is at most derivative bound over k factorial times x to the k. And let's say k is even, so I don't need an absolute value. And similarly, I tilde c of y is equal to qk minus 1 of y plus minus I tilde c k infinity over k factorial times y to the k. And then when I take the expectations and take the difference, that cancels because these are equal under ky's independence. And I'm left with something, and these two expectations are the same because it's also under ky's independence. So this is at most 2 times the derivative bound over k factorial times expectation of x to the k. And k factorial is basically k to the k. This is at most 2 to the o of k times. This thing is at most 2c to the k. This thing is at most, this thing is like k to the k. This thing here is like root k to the k. That was Khinchin's inequality. Times root k, all to the k. So that's at most 2c over root k to the k. So set k to be something like c squared. Okay. So the key here was that this decays as k increases. So I can set a k to make this as small as I want. The problem when you move to higher degree is that this thing actually, so this is degree 1. This thing actually becomes at most k to the dk over 2. This is from hypercontractivity. Okay. So already if d equals 2, this becomes a k. And you don't gain anything by increasing k. Okay. In fact, it becomes worse. Good. So the proof that I'm going to show you is basically engineered around this. Okay. So the goal at the end of the day is we're still going to try to create smooth functions and Taylor expand and whatnot. But we want the moments that come out of our Taylor error to not be the kth moment of some arbitrary degree 2 polynomial, because that's troublesome. Okay. So okay, yeah. So what's the plan? Let me show you. Okay, let me say a word about the plan. The plan for degree 2 specifically. Or let me say a very vague general plan in life. Okay. which is I know what you wanted. Okay. So here's one plan. What do we actually care about fooling the indicator function of? So really, remember, x and y. I mean, we reduced it to some one-dimensional problem by fooling the indicator function of an interval evaluated at some degree 1 polynomial, right? But why did, maybe we shouldn't reduce it to some degree 1 problem. Maybe we shouldn't reduce it to a one-dimensional problem. Let's work in the original dimension, which is n, right? So we have x, y, which are in -1, 1 to the n. And we have some function mapping -1, 1 to the n into 0, 1. Okay, like the indicator function of some set. So really what we want to show is that the expectation of the indicator function of the set f inverse of 1, which is a set in Rn, evaluated at x, is roughly the smooth version of that f inverse of 1 at x. You see what I'm saying, I guess. Why don't we do something like this? Okay. Why don't we do something like that? Huh? Yeah. Well, I guess it is true. I mean, for our f being the degree 2 PTF. Oh, wait, I guess some steps might not be true. I mean, this is approximately that. That's true. But maybe the intermediate steps are not true. So, and this is better because if you do like Taylor's theorem, like the multivariate Taylor's theorem, you're going to end up with your error is at most a sum overall multi-indices that have a total sum of k of this derivative of your function I tilde c over a beta factorial times x to the beta. So these are multi-indices. So in particular, what I mean here is the product over I of xi to the beta. I, and I mean here the product of beta I factorial. Okay, yeah. The indicator function of f inverse 1. Well, f inverse 1 is the set of all x's that make f equal to 1. So I want. No, so this evaluates to 1 if x makes f equal to 1. Oh. Yeah, I see what you mean. Yeah, that's true. So yeah, so I guess I want to say that. Yeah, so I guess this is really just f of x. That's true. But yeah, I'm happy with that. I don't know.
Okay, but you want a multivariate expansion. Well, the Fourier would only give you multilinear polynomial.
You're talking about the move from here to here, or the move to the polynomial at the end?
Well, the Taylor expansion that you were.
Oh yeah, the Taylor polynomial.
Now, you can't do Fourier because that will not give you the higher degree coefficient. It will only give you a multilinear polynomial.
Oh.
No, but higher powers of
Higher
x.
powers of x.
You can get it not from the original function, you wouldn't get it, but from the approximation you might get it.
You can still do Taylor expansion, right? You don't have to do Fourier expansion. It's just a continuous function.
But somehow this isn't really using the fact that you're the sine of a
Right. Well, I
The
mean,
reason why you
yeah.
wanted to go to one dimension in the first place
Right.
is that
No, I mean, this is not going to work.
you're mapping this high dimensional space by this small polynomial into a one-dimensional space.
Right. Yeah, I mean, yeah. What I'm saying here is like, I mean, it's not going to work. It's semi-bogus. I just want to point out. Well, it's not okay. It's not completely bogus. It's bogus in the sense that it doesn't work, but it's not bogus in the sense that it's it suggests that maybe
Is somehow
there.
the intuition that the x to the beta is going to behave for many betas like not like k to the k over 2?
Right.
Behave like exponential in Kane's?
Well, I mean, in particular, if xi is a random plus minus 1, xi to the beta absolute value is 1, right? So you moved from you used to have a root k to the k, now you have 1, no matter what your function is. Okay, so this root k to the k doesn't really have to be there in some vague way. Okay. I'm not sure if writing this helped. At least it helps me. It helps me personally. I thought I would share it in case it helps you somehow, but.
So what will
So,
happen will be similar to that.
well, we'll move to higher dimensions. We're not going to do this, but
So, okay, now you talked about the intersection of half places.
yeah,
Spaces. So then it would make sense if you have m half spaces
yeah,
to be looking at the function as an m-dimensional function.
yes, yeah.
Then,
And we're going to do that, actually.
okay.
Yes, we're going to do exactly that. Okay, good. So I'm going to erase this just because it's semi-bogus anyway. And let me state another FT-Mollification theorem. So another theorem.
Just before the, since you are going to do the intersection of whatever half spaces or in general, it's just the intersection of some events.
Yeah.
Can't you use just the general principle that k-wise independence fools well intersection of k events by inclusion exclusion? You get if you just you have some
Like
k- what?
These are not disjoint sets of variables.
So you're saying that you're looking at. So what are you taking inclusion exclusion
For the event.
for? Which event?
So in this case, the indicators of the half space.
So are these actually pairwise independent?
Ah, so they will not. Okay, so the variable. Okay, sorry. Yeah, good.
Oh, okay. Yeah. Although we're going to use that, we're going to use some inclusion exclusion later if we get to the stable random variable stuff, but for a different. Okay, okay. So theorem. Okay, so for all s in Rd, and for all c greater than 0, there exists a function I tilde cs mapping Rd into non-negative reals, such that, so 1, if you look at the beta of partial derivative, this is at most 2c to the beta, and 2, I tilde c of x minus I sx is at most the min of 1 and O of d squared over c squared times the Euclidean distance to the boundary squared. And I should say, I don't really mean the boundary. I don't really mean the distance to the boundary. I just mean if x is in S, I mean the distance to the complement of S. And if x is not in S, I mean the distance to S. Okay. Okay. And just reminder, so what I mean, so there's going to be a bit of multi-index notation.
No conditions on S can be created.
Yeah, it can be, well, I never really thought about like what measurability conditions you need or something, but
Well, I mean, you prove this theorem. So what the
And it-
theorem
well,
doesn't use any properties of S.
I guess if S is crazy, the denominator will be.
this thing,
Yeah, that would be very. I mean,
that'd be, yeah, that would go to, okay, yeah, I see what you mean. That would go to 0.
Well, but that doesn't. There's a minimum with 1, so it'll just swamp out the areas where it's crazy.
I mean, at least you have to
But-
assume that S is measurable. Otherwise,
But it's also an indicator function, right? So
I mean, yeah, it would be trivial to get to just get something that's always within 1. So there's no theorem to be proven if S is some very crazy set.
So if you just wanted 1, you could set I tilde c to be 0, if that would work.
Yeah.
Because this indicator function just wants 1.
So just a reminder, so if I say x to the beta, I mean the product over I xi to the beta I. If I say beta I factorial, I mean the product of beta I factorial. And beta choose alpha, I mean the product of beta I choose alpha I, etc. And I think the only other thing I might use is if I look at some partial of f, I mean dx1 to the beta 1, dxd to the beta d of f, and this thing I just mean the sum of beta I. Okay. So the proof of this is very similar to what I said last week, what I showed you last week. So I'll just comment on the differences. Question? I meant the L2 distance, Euclidean, yeah. Okay. So the proof. So let's take a function that looks like this. And C is chosen so that this is true. Okay. And then let's take the Fourier transform of this function. E to the minus I x dot t. Wait, where? Yeah. E? Oh no, it's C, some constant times that. 1 minus the L2 norm squared. And let's call B of x, B of t is b hat squared. And remember also I use this notation, g of cx is equal to c to the d times g of cx. This? Yeah, well, I guess, I mean, it's only over the sphere that it has any mass. Yeah, so I guess I wrote that last week. You could use this too. It's fine. Yeah. Yeah, it does depend on D.
So D is the dimension of the space we are working on.
Yeah.
So that's not the degree of the.
Oh, yes. Yeah. Okay.
You can keep it, but that has nothing to do with the D that we discussed.
Yeah. So from now on, we're only going to be talking about. Yeah. From now on, D is 2. So the other D is 2. So the other D is not a variable anymore. Okay. And then so in general, this thing is just the convolution of f with b sub c. Okay, so B sub c. So you take, in general, when I say G sub c, I mean this thing. Yeah.
Only the normalization is c to the d instead of c that we had last time.
Yeah, to keep the integral 1. Yeah. Okay. So I won't, well, the proof of the first thing is really the same exact thing as last time, where you show that so let me say you have a general f instead of the indicator function. So if you look at f tilde c kth derivative, that's at most equal to what you had last time was, so f infinity times c to the k times the L1 norm now of the beta partial derivative. Oh, so this is not the kth derivative, this is the beta partial derivative. Okay. So this is exactly the same thing as last week, and you just need to bound this, and it's the same exact proof. I mean, I don't know. I'll just skip it. Okay, so I guess I should say something about item 2, because something changed from last week. Namely, there's a d squared in the numerator. So where does that come from? So if you remember from last week, we said that for all x, so we said something like fix x in Rd now. And suppose that there exists epsilon delta greater than or equal to 0 such that if x is close to y in Euclidean distance, that implies that f of x is close to f of y. Okay. So suppose x satisfies this property for some epsilon delta. Okay, then what you have is that f of x minus f tilde c of x is at most epsilon plus f infinity times O of 1 over c squared times delta squared. Okay, now we're going to have a d squared here. And where does that come from? So remember last time, oh yeah, f is just any function. F is a function. So f is a function mapping Rd to R. Not differentiable, but measurable. Not differentiable, but I guess the convolution should exist. Oh yes, that's a typo. Yeah. No. This is f tilde c. Yeah. 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 Okay. So if you remember last time, the way that you prove this thing here is that you just write down what f minus f tilde is. It's an integral. You break the integral into 2 regions. One region is when x and y are close. That contributes at most epsilon. And then the other region is when x and y are far. Here far is far in L2 distance. And then you apply Chebyshev's inequality. You view capital B sub c as a density. And then you apply Chebyshev's inequality to say that you're not large with large probability. So again, it's going to be the same thing again, except now you just have to calculate what's the variance this time. Okay. So for 2, so proof continued. So for 2, we have that f of x minus f tilde c of x, or let me not even put the absolute values yet, is equal to the integral of f of x minus f of y b of x minus y. And then I'm going to split the region of integration between x minus y is small plus x minus y is large. Okay. The top part here is at most epsilon, right? Because these are always at most epsilon and in magnitude. And this integrates to 1. And then this is b sub c. And then down here, you can pull out 2 times f infinity. So there should really even be a 2 there. 2. Well, okay, there's a big O there, so it doesn't matter. And then now, this is at most. I think I can erase this, hopefully. So this thing here, we call this star. We have that star is at most, once you do a change of variables, the probability of u coming from a distribution B that u squared is greater than, or u2 is greater than c delta, which is at most, by Chebyshev's inequality, the expectation of u coming from B of the L2 norm of u squared over c squared delta squared. So now I just need to show you that that thing is O of d squared. So if you look at what is the expectation of the norm of u squared, so the expectation of the norm of u squared is equal to the integral of the norm of u squared b of u du. Okay, and this thing is equal to the Fourier transform evaluated at 0. So what is this thing? This is, so right here, this is equal to, can everyone see? This is equal to the sum over I of ui squared bu. And so when you take the Fourier transform of any one of these, remember if you multiply by u sub I, it's like you do a partial derivative with respect to xi. So, and so you do the partial derivative of the Fourier transform of capital B. Capital B is b hat squared, so its Fourier transform is b convolved with itself. So the second partial derivative. So okay, so let me write some facts. So b hat is equal to b convolved with itself, which implies that ui squared bu hat is equal to the convolution. It's the partial derivative convolved with itself, delta b delta xi or ui convolved with itself. Oh, I should leave that. So that means that the integral of u squared bu is equal to the sum over I of that convolution evaluated at 0 which is the integral of delta b dui evaluated at y times delta b delta ui, or sorry, evaluated at u minus u du. Okay, but because of the function we chose, this is an odd function, so this is just equal to the same thing as that. So we have this thing squared. Okay. Okay, and that's equal to the sum over I of, well, in the unit ball, 2xi, 4xi squared, which is equal to 4 times the L2 norm ui squared. Thank you. U squared. Okay, so now what do we say? Well, oh, I mean, huh? Of the integral of this. Yeah. Yeah. Although you could, it's not crucial. Many other functions would give you a result which ends the same way. Okay, so now how do we bound this? So remember we know that. Okay, so now if you, what's this thing of moving to, it's like the generalization of polar coordinates, hyperspherical coordinates, right? Basically, this is equal to some constant, whatever, that maybe depends on d, cd prime, times the integral over angles, the integral over
What is the measure d?
over rd.
So just the unit.
Yeah, and now I'm switching to like polar coordinates. I mean, yeah. Oh, yeah. That's right. Okay. Yeah. Yes.
Yeah, but this calculation should be a dimension, just a function. It's clear it's a function of the dimension.
Yeah, it is. And we're going to get an answer that is.
So let me understand this integral. We are just integrating over the ball.
Yeah.
The length of u squared, the length of u is on the ball is the unit ball is 1, no?
Inside. Yeah, it's u is inside like.
Yeah, but then you can we have a formula for the surface.
Yeah, there's a formula. But okay, so you could write down explicitly what this thing is, but you don't even need to do that. I'm going to show you that without even knowing what that formula is. This is d squared. Okay, so you switched into like what's your radius and what are your angles, okay, and over the radius r, and you need to put in the determinant of your Jacobian for changing variables, and you're going to get some function of angles, which doesn't really matter for a reason I'll show you soon. So this, just move it out there, times the Jacobian. The determinant of Jacobian also has the radius to the d minus 1. Okay. And then now times, that's the radius squared. Okay. So overall, this whole thing is some CD double prime, once you integrate out the angles and that g of the angles thing, times the integral over r of r to the d minus r to the d plus 1. Okay?
Well, what are these constants like d? I mean, the whole thing will be depending on d, so you cannot know.
Yeah. Oh, yeah. It's trust me for a second. Okay. I don't know. We don't even have to think about it because remember we normalized b so that it has square integral 1. But also, if you look at the integral of b squared, that's equal to the integral over the ball of 1 minus u squared, which is integral of 1 minus 2u squared plus u to the 4th. So we can again switch coordinates, and this thing is equal to the integral. So again, we have that same constant CD double prime. It's the same constant, which is why it doesn't matter what it is, because we're just going to compare the ratio of this to that. Of r to the d minus 1 plus or minus r to the 2r to the d minus d plus 1 plus r to the d plus 3. R is going from 0 to 1 because we're in the unit ball. dr. Okay? So what's this thing? So we can just integrate it. So that's r to the d over d minus, I'm sorry? 1 over d?
No, the integral is 1.
Yeah, so it's gonna, yeah, so it's, I might as well put r being 1. 1 over d, is that what you're saying? 1 over d minus 2 times 1 over d plus 2, or let me, minus 2 over d plus 2 plus 1 over d plus 4, which you can combine and get something 1 over d to the 4? d cubed. Yeah. Is that really what I want to say?
Yeah, this is 1 over d cube, and that's 1 over d plus 2. So this is a factor of d squared.
Yeah, so this thing gives you 1 over d plus 2. Ah, good. Yeah, so there's a factor of. No, but I need to actually compute. I need to actually make sure that.
I mean, this is a constant over d cubed.
Is it a priori clear it's a constant over d cubed?
Yeah.
Really? You have to calculate it. Okay. Yeah, you need terms to cancel when you like actually combine these fractions. They do. Okay, and so that's the proof of it. Okay.
Oh, I see. Otherwise, we would have to calculate this variable constant in front of little b. But if we were trying to just evaluate the integral directly, we would also need to know the constant in front of.
Right. I mean, you could look it up. It's known. This is something, but yeah. So okay. So anyway, that's how the proof goes. Okay. So now let's use it to fool the intersection of m-half spaces. Actually, let me do the following. So
Is this function b the best possible in terms of the bound you get there? Or is it possible that there will be another function which will be infinitely squared or something like this? New function b that you pick for this bump function. Is it possible that there's a better one?
I don't know the answer to that.
Do you want to take a break or it's just continue?
I can keep. Yeah. Or is it? Are people?
No, you're on the boss.
Oh, is it? I mean, are people tired? Anyone want a break? What? Oh, you're tired? Huh? Okay, so let's do intersection of half spaces. And just so I can show you, let me just do it where they're Gaussians. Okay? And notice that, say, for Gomez-Williamson, it suffices to fool the intersection of two half spaces. I'll just make that statement. That's true. Although there are better ways to de-randomize Gomez-Williamson than that. Right? Because do people... Well, okay, let me just write it so GW. So right, you have these edges that got turned into vectors. So M edges, they're all in some high-dimensional space, I don't know. And what you want, so cut edge, if and only if the sign of G dot x, so let's say cut edge ij, if and only if the sign of G dot xi is not equal to the sign of G dot xj. So I can define my half spaces hi is a set of G such that xi dotted G is greater than 0. And then really I want to fool the indicator function of, so ij cut if and only if the indicator function of hi intersect hj at G plus, or the other way is that you have hi complement intersect hj complement of G is 1. And I mean, this is pretty much the same thing, except instead of greater than 0, it's less. So fooling things like this is really what it boils down to.
But it's hi intersect hj, not hi intersect hj complement.
Yeah, cut. Yeah, sorry.
Okay, yeah, whichever. Okay.
Yeah. Yeah. Yeah, I mean, it turns into less than 0. Oh yeah, that's it. Just I guess also just it is. Okay, good. So let's fool the intersection of M half spaces. And also note additive approximation of this expectation is sufficient since, say, max cut is at least half the edges anyway. So I mean, to get multiplicative approximation, it suffices to additively approximate that expectation. So theorem. M to the 6th over epsilon squared y's independence suffices to fool intersection of M half spaces. In fact, there's an optimized version of the proof that can even...
Are there other ways to de-randomize Gomez-Williamson that are just based on dimension reduction, or?
Well, I guess I think there are several de-randomizations out there. One clean one that I'm aware of is by Siva Kumar, which uses that RL is contained in SC. I see. Okay. I see.
You can do it just with Willy.
Okay, so let's prove this. Okay, so Okay, so proof. So let S subset of Rm be the set of Z such that for all I equals 1 to M. So my half spaces, let's say my half spaces are, they look like ai dotted with x should be at least theta. Those are my, and I have I running from 1 to m. Those are my theta I. Those are my m different half spaces. For all equals 1 to m, I think just z is greater than or equal to theta I. Okay, and also let me define a map.
You're going to use Gaussian method?
Yeah. Capital F. Thanks. Yeah. And capital F of x is equal to a1 dot x, am dot x. Okay, so really, what I'm going to show is that the expectation of the indicator function of s evaluated at f of x is close to the smoothed version. And then you can move to KY's independence. And then back to the original function. Okay, and let me label these things so it's. Just that all the marginals on k variables look exactly as they should.
So there isn't necessarily a efficient construction, but you don't need it.
No, I understand. It's not clear that, I mean, sort of a priori, it's not clear that there is some distribution that has this property.
In fact, you cannot get this without getting full independence, right? Because the Gaussian.
Yeah, exactly. So
Wait, if Gaussian's what?
If you have pairwise,
Here.
if the correlations are zero, then
No, that's only if they're independent.
That's what a Gaussian said.
That's only if they're independent.
I mean, suppose you need L bits to generate a Gaussian in one dimension. Why can't you use KLY's independence?
Yeah. But even
But
it's
that's
just
still
that
with
you
some
actually need infinite number of bits to generate a Gaussian.
Exactly. To generate
but
a
Yeah.
still, if
but to
you
approximate it.
but to approximate it, right?
Yeah. So I guess in real life you would do this to finite precision, and then I mean, for any random variable, you can generate it with a uniform random variable by inverting the CDF. Okay, and there are efficient ways to.
I'm just trying
yeah.
to imagine how does a KY independent Gaussian distribution looks like. I mean, okay, you said, okay, the marginals look like like they should.
Yeah.
But I'm still there. I mean, KY's independent distribution, we have very efficient descriptions of, in fact, K polynomials I evaluate.
I see.
So is there an analog description for KY's independent Gaussian that somehow approximate KY's independent Gaussian that obviously is not a full dimensional Gaussian?
So I guess the question is equivalent to how do you generate KY's independent uniform 0, 1 random variables? Because once you can do that, you can generate KY's independent any distribution.
No, I believe it can be done. I'm
Yeah,
wondering
so
how if there's some description that's obvious
for uniform random variables.
No.
Oh.
For KY's independent Gaussian,
if
that
you only want,
clearly looks like what?
if you want approximation, you can take a matrix where every k columns are like n by m matrix, where every k columns are almost like have very good condition numbers, and then multiply it with a
Okay,
random
got it.
function.
Yeah, that's good. Yeah, so that's the analog of the K. Yeah,
That's what happens
the
with the
independent, the Boolean one.
Okay, so let me prove some inequalities. So again, I'm going to show, well, the difference of the expectations is at most the expectation of the difference, which is at most the probability that the distance of f of, this should really say g. And let me call the KY's independent version h. f of g to the boundary is less than rho times 1. So this is some parameter which I'm going to set soon, plus that big sum again. Okay, good. And so now, here's the thing. The distance, of f of g to the boundary well, let me just say in general, suppose you have a vector z. What's the distance of z to this boundary of S? Well, it's at least the minimum over I from 1 to m of zi minus theta I. So that implies that the probability that the distance is less than rho is at most the minimum of f of gi is less than rho, which is at most the sum over I, the probability that f of gi is less than rho. Okay. And this thing is just at most m times rho. So I'm going to set rho to be epsilon over m. Yeah, so you can get m to the fourth, but we know how to get m to the fourth, for example, and maybe it's possible to get better. I don't know. I just want to show you an example of applying that theorem before I move to the degree 2 polynomial. Well, we're gonna lose another factor of m in the Taylor theorem thing. Oh, I see. I see. I guess. I see. Yeah, I don't have a counterexample to that. And you have a PRG for them, right? Okay. Somehow I need to think again. I thought at some point I knew that you needed m squared over epsilon squared, but I could just be misremembering what I used to know. Okay, so maybe that's not true. So anyway, so this I don't want to get bogged down by details because we have 45 minutes left. But basically, you set rho to be epsilon over m. You set c to be m over rho. Okay, and then when you do Taylor's theorem, so for Taylor's theorem, you get that the Taylor error is, so let's say you just look at the Taylor expansion of I tilde s c evaluated at some z. The Taylor error of that is at most the sum over all multi-indices summing up to k of a bound on the derivative over beta factorial, which is the product of the beta I factorials, times x to the beta, which is the product of xi to the beta i's. This thing you can pull out is at most 2c to the k by our theorem. And so this thing, and this thing is at most, you can pull it out. That thing is at most x, I said z, didn't I? That's at most the L infinity norm of z raised to the k. So then this thing, and what I'm also going to do is I'm going to divide by k factorial on the outside and then multiply by k factorial on the inside. So this is at most 2c to the k times the L infinity norm to the k over k factorial times a sum over b equal to k of, I divide by k factorial and I put in a k factorial, and now this is a multinomial coefficient. K chose beta 1, beta m. This is just equal to m to the k, right? I have k objects, and I want to, how many ways can I put them in m bins? So this whole thing is, and then again, this is at most z1 to the k plus z2 to the k plus zm to the k. So this is at most 2c up to 2 to the o of k terms, 2c over k to the k times the sum of zi to the k. K is even. Okay, now what are my zi's? They're these linear forms, ai dot g. Okay, so ai dot g, its kth moment is at most root k to the k, and there are m of them. Oh, and there's an m to the k. I forgot to write. There's an m to the k. 2cm. So this thing is at most m times 2 to the o of k times 2cm over root k to the k. So that implies that k should be at least c squared m squared. So if you track things, oh, it doesn't, oh, no, no. So you can't see that, can you? So that right here says that rho was equal to epsilon over m, and c was equal to m over rho, which is m squared over epsilon. Is that right? And then now we're saying that k needs to be c squared m squared, so that's equal to something like m to the 6 over. Okay, good. So I didn't lie. Okay, good. So I'm not going to do the last step. It's similar to things we've seen. So now let's move to degree 2 polynomial threshold functions.
Can you explain intuitively, so where did going to higher dimensions help, or is it just then in this case, since the degree is 1, it's just a generalization, and you sort of had to go to higher dimensions because rho is the inner intersection with that.
No, but he's using sets in high dimension. Using a set, this says this was a set in m-dimensional space.
Right, and so
And it seems
when
like
you're
doing
looking
the,
at intersection,
the multivariate, it seems like it's a multivariate Taylor thing, which saves you there because you're just paying the original, the one-dimensional root k to the k
Right.
times as opposed to
right.
Yeah.
But that's because we're in the we're in the degree 1 case still.
I'm not sure this is but I don't know.
So if we go to the degree 2 case, it seems like you're still going to pay the same. If you
Yeah.
tried to use
Well.
this argument,
Right. Yeah. So it's not.
you would blow up by a factor of m, and you would go to k to the k, and that would.
Oh, okay. You'll see.
Even
You'll.
for degree 2,
Yeah,
yeah,
what is
it'll
m?
still be very different even for 1.
Yeah, I haven't told you what m is. I haven't. Okay. So let's just see what we're gonna do here. Okay. So. So first, let me just say that by theorems of, so there's Diakonikolas, Servedio, Tan, and Wan, and also Harsha, Cliva, Mecca. I don't want to go into. Maybe if we have time, we'll come back to this. But suffices to consider the regular case. So let me just assume that whenever I want the polynomial to be close to a Gaussian and anti-concentrated, it will be. So I don't have to keep track of all of that. Okay? And And actually, there's a more recent theorem by Daniel Kane, which gives some better parameters for this. But let's just pretend everything is regular. So let me write the theorem now. O of 1 over epsilon to the 8 y's independence fools expectation of sine of p of x for a degree of p equals 2. Okay. So proof. Good. So before I say the proof, let me say a theorem. Otherwise, it's not gonna be clear why I'm doing what I'm doing. So the theorem. So first off, there's a theorem by Hansen and Wright, and it actually has a very short proof. Maybe I'll do that at the very end, which says that if you look at the expectation of x transpose AX to the K, where A is a real symmetric matrix, this is at most some fixed constant to the K times the max of the Frobenius norm of A times root K and the operator norm of A times K to the K. Okay. So now, remember I said degree 2 polynomials, they could have moments K to the K, but this says that that's not always the case. So, it could be Gaussian, it could be random signs, any sub-Gaussian. Okay, so now let's use this thing. So we're going to write P as Q plus P3 plus some constant theta, P4. So this thing is a quadratic form. This thing is a linear form, and that's a constant. And then now, so Q of x is equal to x transpose AX. And that's, this thing A is equal to Q transpose lambda Q for some diagonal lambda. And we're going to write lambda as lambda 1 minus lambda 2. Sorry, this should really say, so what's the expectation of, this is really a central moment bound. So it says that you're concentrated on the expectation. The expectation of x transpose AX is the trace of A. So minus the trace of A to the K. Okay. So lambda I'm going to write as lambda 1 minus lambda 2 plus lambda 3. Here, I'm going to put all eigenvals that are at least delta. Delta is a parameter in the proof. Here, I'm going to put all eigenvals less than minus delta. And I'm going to put their magnitude. And here, I'm going to put the rest. So lambda 3 only has eigenvalues between minus lambda and lambda. And then now, when I undiagonalize, this gives me 3 polynomials. So this is equal to P1 minus P2 plus P3 plus P4 plus theta. Yeah. These are positive semi-definite matrices, positive semi-definite. And also, smallest eval is at least delta. This small eigenvalues. No, but the next thing I do will. So you asked what's M. Yes, M is 4. Yes, although I'm going to do something. Basically, P3 has small moments because of Hansen-Wright. But P1 and P2, I mean, they have the large eigenvalues, so their moments are not small. I normalized P to have total variance 1, so it's at most 1, yeah. So yeah, so here's what I'm doing. So S is the set of Z's in R4 such that Z1 squared minus Z2 squared plus Z3 plus Z4 plus the trace of lambda 3 plus theta is at least 0. And my map M of x is equal to square root of P1 of x, square root of P2 of x, P3 of x minus the trace in P4 of x. Okay? So intuitively, why am I doing this? Well, I got screwed last time because when I did Taylor's theorem, my moments were large. That has small moments. That's really like the k over 2th moment. So it's really like k over 2 to the k over 2, which is like root k to the k again. Yeah. Oh, yeah. The trace of. Yeah, but that doesn't mean that the trace of P3 is 0. Right? Yeah. Okay, good. And then I'm going to show the usual thing that the expectation of I S M of x is roughly, etc. expectation of I S M of y. Okay, so one thing that might not be clear now is I'm saving by doing this square root trick. So why did I even need P3? Why didn't I just put all the positive
What bothers me more is why should it work? You have a quadratic, you take a square root, it's like linear.
So yeah, the square root is why. The square root is why I took P1 and P2 to be positive semi-definite, so that the square root is always real. Because I proved these derivative bounds over, this is a real function over the reals. Yeah, but, and then there's the question of, okay.
Yeah, I know, I understand, but let's just assume that P2, P3, and P4 are 0.
P2, P3, and P4?
Yeah, maybe. I mean, it's a special case. Right?
Okay.
Okay, why does it work just in this case?
Because then P1 will be a low rank matrix.
Why?
Because the Frobenius norm is at most 1 and you have delta, which is each eigenvalue is at least delta. So you can have at most 1 over
1 over
delta.
delta, I see. But the Frobenius
Is that
norm.
why?
Well, okay, so the thing about no eigenvalues are too small is, so there's the step where I do Taylor's theorem and I want that to be small. That's fine. But then there's also the step where I want to say that I and I tilde are close to each other. And for that, I need to talk about the distance to the boundary. And you can get screwed in the distance to the boundary if you have small eigenvalues. Which is, I guess, we'll see this. Huh?
Let me try to get an intuition and tell me when it's wrong.
Okay.
So like one case is if P is the product of two linear polynomials.
Okay.
If P is the product of two linear polynomials, then we can like go, it's going to work out the same as if is this the intersection. It didn't really matter that we were combining things with
Although it wouldn't be exactly the same because there's this issue of just the first inequality. To show that these two are, I mean, what would your set be? What would your set in R2 be? It would be like, it'd be like Z such that Z1, Z2 is positive. So then now you need to talk about distance to the boundary of this region, right? And when you move,
if both are positive by a certain amount or both are negative by a certain amount, that's going to bound the distance to that region.
if both are positive, yes. But then well,
So if you look at, you
well,
bounded it by the minimum, so I think that's still going to be
no,
fine.
no, no. So there's this issue that if Z, so suppose you change Z by gamma in L2 norm, right? How much can you change Z1, Z2? You can change it by gamma times Z1 plus gamma times Z2.
Still, the distance from Z1, Z2 to a place where the sign changes,
Yeah.
it's at least the minimum. To change the sign of the product,
Yeah.
you have to change the sign of one or the other.
Then you
So
can
your
Uh,
use of the minimum is
Oh, I
still
see.
going to work for any kind of function.
Okay, for this case, yes.
No, for any combination, is to the minimum. To change.
I mean the product of any number of linear
No, any
functions.
Boolean function.
Yeah.
Of a set of linear functions. Because you say to change the value of the Boolean function, you have to change one of those signs.
Mm-hmm. I see.
So it's going to be at least the minimum.
Okay. Yeah.
So that part works as the same, I think.
Okay, so now the
Well-
quadratic function will be a sum of several.
Well, so that's what I thought might happen. But here you're trying to say instead of like log n, which is what you would take to cover a.
No, you don't, because of this Hansen-Wright. You can take a constant. I guess that's what Raghu was saying.
Yeah.
You just you can cut it. Well, this product of pi p1 p2s have weights, and you take those that you separate those that come with big weights. And so it will be, it's really a low rank approximation of this quadratic polynomial, right?
What are you saying is a low rank approximation? The square root business?
The composition is really a low rank approximation. P1 and P2 are the low rank part, and the rest is the low
Oh,
the low norm one.
yes.
So you have low rank, which will give small Frobenius norm, and low spectral norm one. So it's okay. But good.
Yeah, I guess although, well, okay.
I don't see, maybe I'm confused. I mean, once you take the square root, it's not a polynomial anymore. So
Yes, but
Well, when you change the basis, I think it might be.
it's not.
it won't be a polynomial.
It's not a polynomial. So when you Taylor expand, but the thing is,
yeah, so why is y and x the same?
so yeah, so there's this issue that when you Taylor expand, you need the Taylor polynomial to be fooled by ky's independence, and that's true because, well, it's a polynomial, but now our function, our I tilde function, is going to be even in both the first and second coordinates. So yeah, those don't appear. Yeah.
Why is it? I mean, you just took a square root of PSD. It's a bilinear form. You get a bilinear form.
You take the square root of the value, not the square root of the matrix.
Oh, it's right. Okay.
No, the I has to be an even function.
It has to be even in the first two coordinates. Yeah. Yeah, it is. Okay.
Then is that also going to be the case with a smooth approximation? Is also going to be even?
Because it's just a convolution.
Yeah, it is.
The little b was even, so everything.
But so couldn't you take, instead of the square roots there, take the square root of the PSD matrix? So have another transformation. So the z's.
That would still be a quadratic form then, and you get the k problem.
No, you don't, because it will have a
You're taking the square root of that, you're saying?
Yeah, yeah. So you apply this to it. This will be your Bernoulli form applied to it.
Then how do you relate this to the original polynomial?
So don't, I mean, the original polynomial was p1 plus minus p2. So that's what you want to recover.
I guess what should your region S be?
Oh, so now you do the linear form. Square root lambda 1 times x.
Yes,
Square root of?
lambda 1 times x.
Like this?
Yeah, so
That's
then
a mate. That's not a number.
it's a vector. Oh, I see. Yeah. The norm squared is what we want. It's a vector. Yeah. Actually, it's a small vector. If you are willing to throw 1 over delta coordinates, then it will be fine.
No, but I mean, what can you tell us what delta? How should we think of delta as a function of the other parameters? You said it should be chosen as a
Yeah, so delta is we're gonna later choose it to be polynomial and epsilon. Okay, so maybe I should start writing proofs. So let's do item 1. Okay, so again, we have the usual stuff that the difference of the expectations is at most the probability that the distance from m of x to the boundary of s is at most rho plus this big sum, etc. That's going to be geometric, whatever. And then, of course, as usual, we're going to have to set c to be something like 1 over rho. And now we just need to understand this thing. Well, the distance from m of x to the boundary of s. Well, let's just look at an arbitrary z to the boundary of s. So remember, what do we have? We have this z1 squared, etc. Now suppose that we change z by some vector u, some vector which has at most L2 norm u. Then we change each coordinate of z by at most u. So that will change by u times z1, and that will change by u times z2 by u, etc. Oh, and also there's a u squared there, right? If you change z1 by u, z1 plus u squared, you have the z1 squared plus 2z1 plus u squared. So
Basically, what do you use union bound over different coordinates?
a union bound over different coordinates. Wait, what do I want to do? Let me just think for a second. So, okay, let me write out what I'm thinking. So, if I change z by u in L2 norm, I change each zi by at most u. So this expression here, let me call this expression star. Star changes by at most. This gives me a 2z1u plus u squared. That again gives me another 2z2u plus u squared. And that changes by at most u. Right? And then now, so that's equal to 2, that's at most 2u z1 plus z2 plus 1 plus 2u squared. Okay. So really the argument is going to go like, you're going to have a tail bound for P1 and P2, and you're going to, well, Z1 and Z2, you can't see the bottom of the board. Okay, so the argument is going to say, first we're going to apply a tail bound and say Z1 and Z2 won't be that large with high probability. Oh, is it? So that's good. Oh, okay. Okay. So let me say the probability. So lemma. Well, okay, before I do that, let me just say then that. So the distance from z to the boundary of S is at least 1/2 times the min of z1 squared minus z2 squared plus z3 plus z4, etc., over 2 z1 plus z2 plus 1. And the other term there was like u squared. So the square root of z1 squared minus z2 squared plus something like that. Okay. Thank you. So I can apply, I guess I never wrote the theorem down, but there are theorems for anti-concentration for higher degree polynomials by Carberry-Wright, which says that the probability that your polynomial is in it, yeah. Oh, I did write that down, yeah. So you can do that here, and you'll get whatever this is to the 1/4, right? Because there's a square root here. And then here, what you'll do is, remember, z1 corresponds to p1 of x, z2 corresponds to p2 of x. If I can apply some lemma, which is a tail bound for p1 and p2, then these things are not that large. Okay, so I'll condition on z1 and z2 not being large. So lemma is that the probability that p1 of x is greater than c over delta, and it holds for p2 as well, is at most exponential in 1 over delta. And why is that? So I don't want to, since I'm running low on time, I'll just sketch it. Basically, the trace. So okay, so P1 has a constant term, right? Because
But in general, if delta was 1, though, it would be just one coordinate, and this would be just multiple.
if there's just one coordinate, yeah, I guess.
So you have delta coordinates.
Right, I have delta coordinates. Right. So basically, the constant term in P1 is at most 1 over delta by just looking at it follows by Cauchy-Schwarz. Basically, right. This has at most. Do I need to say anything? Right. So the.
But we really need something exponential in 1 over delta. We wouldn't be happy with a polynomial.
Yeah, that's.
So, I mean,
Yeah, it's overkill, but it's true. Okay, so basically the constant term in P1 is at most 1 over delta. You can show this by Cauchy-Schwarz, looking at the trace. trace of lambda 1. And then the polynomial part of P1 is at most 1 over delta with that probability, with high probability by, well, by just applying, say, you can apply Hansen-Wright or whatever, even the k to the k bound that you had for polynomials by degree 2 tail bounds, generic degree 2 tail bounds. Okay, so that implies that the probability that the distance from x of x to the boundary of s, well, the probability that is less than rho is at most the sum of the probabilities that either of these things is less than rho. The probability that this is less than rho is at most rho to the quarter. The probability that this thing is less than rho, well, okay, so first we have this condition, so x of minus omega 1 over delta, conditioning on that event, plus, so these things are each at most, plus in, I think rho times, sorry? So it's rho times root p1 of x plus root t of p2 of x plus 1. The probability that you're less than that, but this thing is like root 1 over delta, right? This thing is also root 1 over delta. The probability that you're less than this thing is like root p over fourth root of delta. Is that what you said? Yeah, so I mean the probability that you're less than that. So this thing is at most root rho over delta to the quarter plus root rho. Well, but that's dominated by the rho to the quarter anyway. Okay. So this is telling us that we should set rho to be something like epsilon to the 4. Well, we haven't set delta yet, but that's telling us that rho is going to be at something like epsilon to the 4th, or maybe even less later. So what does this tell us we should set? Rho should be less than or equal to, what did we have before? That c was, before we had that c was 1 over rho. Rho has to be less than or equal to epsilon to the 4th power, and also e to the minus 1 over delta should be less than or equal to epsilon. But there are going to be some other constraints too. Okay. And also rho squared over delta to the quarter should be less than epsilon. There you go. I think I have until what, 12:30? Okay, so I mean, from here on out, it's really going through the same steps that you've kept seeing over and over again, and keeping track of parameters. I mean, so
Just
tail.
like in the, so where are we using, so maybe just in a high level, so where are we using, okay, so you said the distance to the boundary is probability rebounded by some kind of
Yeah.
anti-concentration.
But and notice it depends inversely on delta, which is why you can't just put all the positive eigenvalues in one matrix. This is why we need P3.
Oh, yeah, sure. Why we need P3.
Yeah.
Then you need to bound the expectation of this vector to the k.
Right. So remember before, when we had the half spaces, intersection of M half spaces, we had that the Taylor error at the end of the day was at most something like 2c to the k times the dimension to the k, which is 4 here, over k to the k, times so z1 to the k plus z2 to the k plus z3 to the k plus z4 to the k. And this is, remember, this is root p1, so it's like p1 to the k over 2. Also p2 to the k over 2. This is going to be p3 minus the trace to the k, and this is going to be some linear form to the k. This is like delta k to the k by Hansen-Wright, or the max of that in root k to the k. This is like root k to the k, and that's like root k to the k. And delta, okay, and k, remember k is poly 1 over epsilon. Delta itself is poly epsilon. So this thing is going to be better than k to the k. This is going to be k to some power to the k. What? Sorry, say it again. Oh, what, you mean the value of k?
The value of delta has to be
Oh, I see.
1 over 8c.
Right, so c is 1 over rho. I think I'm also going to choose delta to be 1 over rho. Or delta to be rho, I mean. Rho over 8, is that what you said?
Oh, you want 16 to be safe.
Okay, well, yeah, okay, fine. I mean, I also get to choose k. I can put a constant in k. Okay.
So you didn't really use that, the first part as lower end. It's just
We
that
implicitly
it's
used
far
it.
from the boundary.
We implicitly
Just
used it in the calculations for saying that it's far from the boundary.
Or with the Cauchy-Schwarz.
yeah, with the Cauchy-Schwarz, I used that as low rank.
So, is it true that an alternative proof would be just to take the low rank part and treat it as, so it will increase your dimension, but you'll have just a rank 1 part, which is just a single variable square.
So you're saying, so like, I mean the proof where, like, say you take the large eigenvalues and shove each of the large eigenvalues into their own coordinate.
Yeah, on coordinate.
Yeah, and create many dimensions. In fact, that idea is the starting point for how Daniel's proof works for a higher degree.
But then you wouldn't have this problem with the square root. It will be a polynomial. It's the square root of a variable, so it's just a variable, right? And
Yeah.
this variable, in fact, its expectation of the kth power, but there will not be any sum there. There will not be any.
Yeah, that's true.
So you lose on the m, but you may. I mean, maybe it's it's the same. Maybe it's the same proof, but I mean, maybe it's. I don't know. No, visualize a bit better because every rank 1 is just a variable. Single variable. Like in the Gaussian case, it doesn't matter that you're.
It's a linear form because
It's a linear form.
it's a linear form.
Yeah, but it's in the Gaussian space, it doesn't matter because it's a Gaussian. It's a Gaussian, it's in one-dimensional Gaussian.
There could be
Oh, it's a
correlation.
Gaussian
Oh, so you're
What is
saying
it?
moment calculations we can view it as just a
Exactly, yeah, the moment calculation. It's just a Gaussian of standard deviation 1. I mean, because of the.
Yeah.
We normalize
So you can make a proof like that work.
So this could require, I mean, once you, if you can make a proof like that, so you never directly use the, you know, the Hansen-Wright, you never really use the Frobenius norm bound.
Yeah, I guess the Frobenius norm of everything I was considering was always at most 1.
No, but in the proof, where did you use this part? So they have a maximum of the
Oh, I see.
spectral norm, and you use the
Well, I
spectral
guess.
norm for S for these 3.
Yeah, I guess this P1, I have no idea what his operator norm is. It could be large. So
Okay, here. So then.
I just use the Frobenius.
Frobenius norm is 1. Okay.
Right.
Yeah. Right. So that's then it's the same. It's the same as the low rank and this.
And yeah, I guess there's not much time left. If anyone really wants, I could show you a proof of Hansen-Wright, which someone showed me, but I don't know. Oh yeah, I can try.
You have 5 minutes.
5 minutes. Okay, I'll show it to you because it uses things that I think are very useful to know. This is not my proof. But I think it's the best proof. Oh no, this is not the Hansen. So there are several proofs of Hansen-Wright. So we actually have our own proof of it. Hansen-Wright had their proof, and then I'm going to show you a different proof from all of those. That, as far as I know, this is PZA's proof, but maybe it's someone else's. I don't know. So this notation, remember, just means expectation of x to the t to the 1 over t. And I'm going to show you this proof because I feel like there are ideas in it that are very useful for things we do in CS all the time. So we have the sum of ij. It's a moment bound. We want to bound the sum of ij, sigma I, sigma j, t. Okay? Okay, I claim that this is at most. Right now they're random signs. Huh? Trace 0. Trace 0. Yeah, I guess in the case of signs, you don't care about the diagonals. Less than or equal to. So I'm showing you this because this uses a bunch of tools that I think are handy. One is decoupling. 4 times the sum of aij, sigma I, sigma j prime, where sigma j prime are the sigma prime is an independent vector from sigma I. Okay. And then this is equal to 4 times pi over 2 times the sum of aij, sigma I, sigma j prime times the expectation of the absolute value of gi, gj prime. These are just this is just a constant, and this is 2 over pi, so I just pulled it out. I just multiplied by 1. I didn't do anything. And then I can pull this out, and that's an upper bound, 2 pi sum of aij. Okay, so I have a random sign. So now I have sigma I, sigma j prime, gi, gj prime. But so there's absolute value here. A random sign times the magnitude of a Gaussian is a Gaussian, right? So this here is just gi, gj prime.
So what did you do? You multiplied by, you introduced independent Gaussians. So
Yeah.
it has nothing to do with the previous time.
That's right.
Really, you get sigma I as the sign of a Gaussian.
Yeah. So yeah, here I'm interpreting sigma as the sign of this Gaussian.
So why is the decoupling true?
Yeah. So I'll prove that. I'll prove decoupling.
You just split at random the set of coordinates at random into 2 sets.
Yeah.
You look at the cross terms. And each term has a constant chance of being a cross term. And once you've looked at the cross terms, they're totally independent.
That's true. Yeah. And then you need to put back the stuff that you lost, but you can put it.
You lose everything with the same probability, so it sort of scales down, and it's only adding it only makes it. Looking at the expectation and renormalizing only makes it bigger. Because you could have cancellation before, but now you can't.
I guess now what I'll do is I can view this as being the sum over j of gj prime, the sum over I of aij gi. Or do I want to do the other way around? Let me do gj prime and gj. Okay? That's what this sum is. So I can treat it as just a Gaussian dot producted with a vector. So this, I can view this as a linear form, right? And then Khinchin's inequality tells me that the moment is like the L2 norm of this to the kth moment is like the L2 norm of this to the k times root k to the k. Or I guess I said t here. So that's at most some constant times root t times the L2 norm of this. So this is just ag. That's the vector ag. And then, so I have this, and then I have that that's at most c root t, and then triangle inequality, the expectation of ag plus ag minus its expectation okay. This thing here is at most expectation of ag to squared square root, which is equal to the Frobenius norm. So you have the Frobenius norm times root t. Here you have, so, oh, I guess this is a proof assuming a tool, namely concentration of Lipschitz functions of Gaussians. Okay, so there's a theorem that says that this is at most root t times the Lipschitz constant. And if you change g by some gamma and L2 norm, how much can you change the L2 norm of ag? That's at most the operator norm of a times gamma. So this is at most operator norm of a. So you get a root t, which is at. Anyway, so I think this idea of decoupling and then doing things is very useful. And it gets used all over the place in some places, so maybe it's good to know. Yeah, it does. Yeah, it does. And the decoupling proof is just in D. Yes, yeah, you do. Decoupling is just, well, I mean, I guess Russell was giving an outline. I'll just write it down because it's not long. So I'll introduce is a 0, 1 random variable with expectation a half. Okay, and now the point is that the sum of aij sigma I sigma j is equal to 4 times aij sigma I sigma j times the expectation of the magnitude of eta I times the magnitude of 1 minus eta j. And then you use the same trick to pull this out. And this just becomes 4 times the sum of, let's say, I such that eta I is equal to 1, sum of j such that eta j is equal to 1, or is not equal to 1, it's equal to 0, of aij sigma I sigma j. And these are just disjoint sets. So you can replace this with this. And then you can add something inside which has expectation 0, because you lost some cross terms by doing this. So what am I going to add inside that has expectation 0? The expectation over the sigmas that don't appear here of sum of aij sigma I sigma j prime over ij not in the last sum. This has expectation 0, and then I can pull that out again.
So it's just writing the
average of things that are bipartite.
Yeah,
That's
Go back. I mean, there are the missing terms.
you count them. You count them, right? I mean, just you have a convex combination whose total weight is 4 times non-convex, or because you remove, or maybe it's 2 only, and you count everything the right number of times. Oh, you need to. Sorry, I see. You cannot do a
only get
triangle
but you have
inequality.
to
Yeah,
go back to
that's
the
right.
same,
That's right. Yeah.
same matrix A. Right.
And I guess there's something that I should have said, which is that because I know this inequality holds, there exists a fixed eta vector which makes this hold. So this is no longer a random partition. This is some fixed thing. And I'm going to put back the things that are missing. Okay. Anyway, maybe it's useful. So.
Thanks. More questions?
I mean, on a very, very high level is that you take this Boolean function and then somehow find a Taylor expansion of it or approximate it. I mean, you do it in 2 steps. I mean,
Yeah.
take the so what is the limit of this? I mean, after all, you are only interested in how where this approximates it on 0 plus minus 1. So you introduce all those regions, but that's not clearly
Relevant, you say?
relevant. At the end of the day, you need some polynomial that approximates this Boolean function well, some low degree polynomial which approximates it well. So there's some general.
I don't know. I don't know what direction to generalize it in. I mean, I guess I used facts about it being a.
Too vague a question.
Yeah, I don't.
Maybe it would be interesting to sort of collect other examples of this. I mean, people approximate Boolean functions by low degree polynomials all the time. This is somehow using analytic tools.
Yeah, I don't know.
I think that you sort of assumed regularity throughout this.
I did, yeah.
I think that the big thing or complicated thing is to get regularity and without paying too much in the parameters. So it seems like this, right? Kane,
Yeah.
general result for Kane is the regularity. So even for degree 2 or even for degree 1 to prove completely just proving half spaces, you need some kind of regularity theorem. And this it gets complicated when you go to degree D. So this analytic part approximation just works in the regular case, and then
I think even the regular case is much more complicated in Kane. So
even the regular case for degree D
is much more because you don't have this kind of.
So the bilinear stops, yeah. The
right,
bilinear
like
is
trilinear, you don't have this kind of eigenvalue decomposition, right? And
Yeah.
some like Latola.
Yeah. So he uses there's some moment bound by Latala for degree D polynomials, which interpret the way Daniel's proof interprets that bound is if your moments are large, it's because you have correlation. You have a good correlation with a product of lower degree polynomials.
It's very simple, similar to what's happening in the finite field case in this green tau and all this.
I see.
Right, I mean, it seems maybe quantitative it looks different, but
I see.
That reminds me. I mean, there's sort of Gauss norm is relevant there.
I see. That Gauss norm is what your best correlation with some low degree polynomial.
So if your Gauss norm is high, then it means that your Gauss this Gauss norm is high, close to 1, then, or bigger than constant, means you have some correlation with that.
It's something which is a
Well,
generalization of a
it's
low degree
something.
polynomial.
Yeah, it's a nil manifold, but it's we call it
some something which is a somewhat complicated generalization of what a low degree polynomial is. But the intuition is that it's
There
like
may
an
be
low degree
the
polynomial.
two things may be related because I mean eventually there too you move to even though the original function is over finite field, you move to you move to the phase polynomials or this nil manifold. They are all
But there you're
over
looking
the
at agreement, like bias in correlation, whereas here you just have like a moment bound. So
But I guess the moment bound tells you that the moment is high if there is something like, so you get this k to the dk over 2 for degree d polynomials. Just like here you got k to the k for degree 2. But you only get, for example, degree 2, you only get k to the k if there is a reason, which is, huh?
it's product of two linear functions or something like that.
yeah, but
Is
these
that,
things
yeah,
appear
so.
also there. I mean, if you look, it's just so I'm wondering how far does the analogy go. So you are saying that for fooling with k-wise independence, maybe we just need the moment bound. But in general, these I mean, there are regular decomposition or regularity lemmas here and are they completely unrelated or are they something to do with each other?
The PTF seem very different than.
It does, but I mean the PTF comes in, you know.
The prime number theorem has a form which is somehow very similar to all of these. It would be nice to get a computer science proof of the
So
prime number
prime
theorem.
number theorem, you mean in the Möbius, just the
well,
cancellation, the cancellation
the
Lilo and
cancellation, yeah. So you take the linear function. So you have a 0, 1 variable or a plus minus 1 variable for each integer. No, for each prime.
for each prime.
For each prime.
Okay.
And now you take the linear function that is sum of log p times xp. And let's make it 0, 1 variable. And then that this sum is less than or equal to n. I mean that encodes all the integers up to n. And now you want to take so you look at that this defines a Boolean function, and then you take for each
So
x
what defines the Boolean function? Whether it's less than or equal to n?
whether it's less than or equal to
Okay,
n.
so that's a hyperplane.
That's a hyperplane, and you look
and
at
it's
all the points
the number
below
of
the
coefficients
hyperplane.
is like n over log n.
Is n over log n.
So that's the number of variables, yeah.
Yeah.
So that's what we need to prove.
And now you take minus 1 to the sum of xi.
Just parity, you correlate it with
Parity, yeah. So you just take parity, and you want to prove that this is not correlated with parity.
So this is the Möbius function you define. It's
Yeah,
function.
yeah. And you want to prove that if you sum it over this domain, then you get lit low n. Actually, you think you might get order of root n, but that would be the Riemann hypothesis. But just to prove that this is lit low n. So that looks very much like in this.
yeah, but you have to understand since your coefficients, I mean, it really depends heavily on the coefficients.
Yes,
the fact
so
that
if
they
the
are log
coefficients
pi
are
for
all
the
equal,
prime.
then it's wrong.
Yeah.
But maybe under some condition that the coefficients are reasonably different, it could already be true. So it's not clear that you have to use anything about the log of the primes as coefficients.
Some of the reciprocal converted.
Maybe just the variance of the coefficients is reasonably large or something.
Yeah,
mark of understanding what kind of
Is this the AC0 and Mobius function, or is this?
oh no, I'm sorry. So, but this is not what was done. Okay, so yeah, that's the AC0